Hello, we are going to do a video on non-invasive ventilation, or what you'll see termed as NIV, or sometimes it's also called non-invasive positive pressure ventilation, or NPPV. So what we're going to focus on today is just kind of a clarification of some of the terms and talk about some of the components of these machines, talk real briefly about the interfaces. We'll cover more on that later. And we're going to define the parts of the Respironics STD machine that we'll start working with first in lab. So what is non-invasive ventilation? It really just means we're giving positive pressure to the patient's breathing without an endotracheal tube or ET tube. And it's really supporting the patient's own ventilation. So the patients are spontaneously breathing, so they still have a drive to breathe. However, they need help with either improving oxygenation or improving ventilation. So one of the first terms is IPAP, which means inspiratory positive airway pressure, and that's the pressure that we get on inspiration that will improve our tidal volume and help with alveolar ventilation, which will remove carbon dioxide. EPAP, or expiratory positive airway pressure, splints those airways open and improves FRC, which is going to improve oxygenation. Pressure support is the difference between the IPAP and the EPAP pressure. This is really the amount of support or help or enhancement of the breath that is given during inspiration. So what's the difference between CPAP and BIPAP? CPAP is really just expiratory positive airway pressure. Again, CPAP stands for continuous positive airway pressure, meaning that it's a continual amount of pressure when the person's breathing in and out without any added support to them when they inhale. So their entire inspiration is based fully on the patient. Primarily, this is used for the treatment at home of obstructive sleep apnea. In the hospital, the main time we're going to use it is on patients with heart failure that really need the most improvement with oxygenation. BiPAP then is bi-level positive airway pressure, meaning we're going to have two levels of pressure, one when we breathe in and a lower pressure when we exhale. And then with BiPAP, we're able to deliver this pressure support. The term we use for the amount of pressure support is something referred to as delta P. Remember, delta means change, so the change in pressure, which is the difference between that IPAP pressure and the EPAP pressure. And how much pressure support we give varies depending on how big a difference that delta P is. So the larger the delta P, the more we're going to enhance each of those tidal volumes that the patient takes in. There are several different modes on each of the various machines, and this is true for ventilators, invasive as well as non-invasive ventilators. But the best way that I think of to, in general terms, think about a mode is basically how the machine is programmed to deliver a breath. So what is activated by the machine for each breath? It really is best thought of as a program or a prescription of how the breath is given. So the machine is going to have a CPAP mode. In a CPAP mode, we're only going to set the EPAP pressure. We're setting one pressure, and that's all delivered. There's a mode called spontaneous mode. Spontaneous mode is where the patient is still triggering breaths, but now we are going to set an EPAP and an IPAP, and pressure support are given in this spontaneous mode. In addition, there's a spontaneous timed mode. Now we're adding, you can see one more variable to this, and that's really where we're setting a backup rate. We're going to set a rate that we don't want these breaths to fall lower than. So let's say the patient is breathing 12 times a minute. We're going to set maybe a backup rate of 10 because we wouldn't want the patient to fall below 10 breaths a minute. If the patient were to fall below 10 breaths a minute and meet that threshold, then the machine would deliver a breath instead of it being a spontaneously triggered breath. The term trigger is really what initiates inspiration. So this is important to remember. Trigger is what initiates inspiration. So we dealt with this when we were working with the IPPB machines. If you remember, we set a sensitivity level that would ensure that the patient would have to trigger the breath by drawing out some amount of negative pressure that we set. On the CPAP and BIPAP machines we're going to be working with, we don't actually set a trigger. The trigger is, so we're not setting a sensitivity. It is built into the machine. It's not a variable we can change. Some of the questions that you want to know about looking at some of these different machines that we're going to be going through is you want to know what modes are available, and what can be tricky about this is that some modes can have the same name but do different things, so each machine has their own definition of what that particular mode might actually do. Can these be used overnight? This is especially true in home use. Can there be humidification added? We'll touch briefly on humidification. Some of them have a battery backup. Some machines have oxygen that can be entrained into the machine, so we're going to plug the machines up to oxygen. Other machines we're just going to bleed in oxygen. We always want to know where the expiratory port is within the circuit. For non-invasive ventilation, the circuits are always just a single tube. So we're breathing in and out through that same circuit. So for that reason, we need to have some sort of leak out, or what's called the expiratory port. What alarms can be set, and are these machines recording any data? So humidification can be helpful in the use with non-invasive ventilation. Our machines here at Boise State don't have humidifiers added, but you may see them added to some of the units that you're working with in the hospital. Primarily because if these are used over long periods of time, it is a lot of airflow. It can become uncomfortable if the airway is dried out more. Almost all home use CPAP machines come with incorporation of a humidification device. Oxygen can be adapted to the machine directly, which some of the later machines we're going to talk about do. The STD model that we'll be talking about first, we would want to use one of these adapters to connect the oxygen into the circuit, and some masks have ports on them, this one being right here by these lower buckles or whatever they are, where we could bleed in oxygen, so we can just plug in O2 tubing to that port to administer a higher FiO2. I mentioned the expiratory port, again, because it's a single limb circuit. It's one tube that we are breathing in and out of. If we didn't have a leak out of that system, carbon dioxide could build up and cause a problem. Obviously, if we're trying to ventilate somebody, we're trying to remove CO2. So it's important to know where that expiratory port is and that it never become occluded or removed. The alarms are critical on these machines, primarily because we are working with patients in some amount of ventilatory failure, meaning they cannot necessarily sustain adequate blood gas values on their own. And so if the patient removes the mask or the tubing becomes disconnected, they can quickly have an accumulation of CO2 and a quick drop in oxygen saturation. So some amount of alarms are critical. There's various types of interfaces. There are nasal pillows that patients can just have two prongs going into the nares. There's a nasal mask pictured here that, again, this would require the patient, both of these two up here on top, require the patient to breathe in and out through their nose only and be able to hold their mouth closed. These are probably the most common types of masks used for patients out of the hospital with obstructive sleep apnea. These two in the lower left are considered what we call full face masks or an oral nasal interface. This is primarily the type of mask we use in the hospital because we have patients really short of breath that have been breathing through their mouth, and we get a little bit better seal and a little bit better operation of the mask if we're covering both the nose and the mouth. This is called a perfora mask. It's kind of considered a total face mask. These seal really well. They look gigantic, but they do work well on some patients because they're able to seal well. We'll talk about masks more later. I just wanted to give you a brief overview of what they looked like. The biggest thing that we worry about is, first off, that we have some amount of seal. Not that it's a perfect seal, they're going to leak some, but we need to be able to have a seal without creating pressure sores or air blowing into the patient's eyes. So this is a bit of an art when it comes to this. But again, the two key factors are we need to have a good enough seal that there's not a huge leak, but we don't want these masks strapped on the patient so tightly that they develop pressure sores or just hate the device in and of itself, because the interface is what bothers people a lot. So now we're going to talk about this Respironics STD model, and my pictures are not super clear. I am sorry about that, but it gives us an overview. This is the machine itself, this cream unit at the top. This is the detachable control panel, and this is the alarm module attached to these units. So this part of this machine could be used independently. Most places that are using them in the hospital have attached them to a cart with these two other components added. So this is the machine we'll be working with. So when we look first, we're going to talk about this airway pressure monitor. This really is the alarm system of the machine. Here we have a manometer. Again, like other manometers we've talked about, the manual manometers are generally going to be more accurate than the digital ones. So this is where we're going to look. And basically what we're going to set here is we're going to set a high pressure alarm and a low pressure alarm with these two knobs. Then we're going to set a delay feature, and really what that does is do we want the alarm to go off if the alarm has been going for half a second, or are we okay if maybe the alarm condition is going on for 10 seconds and then it alarms. So this allows us to set a time before the whatever's causing this alarm to go off, whether it be high pressure or low pressure, for it to play the audible alarm. This button here is an alarm silence, so we can click that to quiet the alarm. And this here in the upper right hand corner is the switch that turns the alarm on. Here is our detachable control panel, and I'm going to go through some of these circled items here. This is the overall display of it. The overview is this control here really just says what will be displayed in this digital control area. So as we move this control around, it can either display the IPAP pressure, the EPAP pressure, the tidal volume, or the leak. So we can just display one thing at a time. Down here is our mode selection. Then up here is the IPAP control, and in previous slides, or in preceding slides, I'm going to go through each of these controls, but I wanted to give you a brief overview first. So here is the IPAP control that's going to set that inspiratory pressure that's activated depending on what mode you're in. This control here is going to set your EPAP pressure. This sets your breaths per minute, and this sets your IPAP percent. And this is somewhat color coordinated. So when we're in the CPAP mode, we're only going to set this EPAP CPAP knob. Then we have a spontaneous mode. In the spontaneous mode, we would set all variables in this lighter green area, which is just IPAP and EPAP. If we're in spontaneous timed, we set these two areas plus this control, so everything kind of in this medium green level. So now we're going to set a backup rate in that spontaneous timed mode. And then the last mode we have here is a timed mode. In that mode, we will set all of the controls, so the darkest green color, and so we set these three controls in addition to the IPAP control percent knob. So that's one quick way to help you determine of what is set in each mode. So this is our mode selection. This is where we're going to change the modes. This really is our most important starting point, because depending on what mode we have set, will determine which one of these knobs is activated. So I might be in the CPAP mode. In the CPAP mode, this control doesn't do anything. The next is our IPAP control. So this is the knob we're going to turn to increase or decrease that IPAP pressure, the inspiratory positive airway pressure. The one right below it is the EPAP control knob. That's the knob we're going to turn to vary the EPAP pressure. This one is the breaths per minute control. We generally are going to set that 2 or so or more units below their actual respiratory rate. We never want to set this more than their respiratory rate. If they have such a low respiratory rate starting off, something below 8 probably, we would not want to use non-invasive ventilation. We need a spontaneously breathing patient, so this is really just as a backup rate in that circumstance where their respiratory rate may fall a little bit low. The next control is the IPAP percent control. This is only active in the timed mode, and it lets us determine how much of the breath is going to be IPAP and how much of the breath is going to be EPAP. And that percentage is also based on the breaths per minute we set. We'll work on this some more in class, but one way to think about this is if you have breaths per minute set at 10, that would give you a total inspiratory cycle time of 6 seconds. If you had IPAP percent at 50%, that would mean 3 seconds of your breath would be at the IPAP pressure and 3 seconds of the breath would be at the EPAP pressure. That ends this presentation as an overview of non-invasive ventilation and an introduction to the Respironics STD.